Namaste. Welcome to this new lecture series on why acoustics. In today's session, we are going to talk about three topics: sound propagation, frequency range, sound versus electromagnetic waves. Coming to the first topic, sound propagation. In the previous session, we heard about the sound traveling in different media like air, liquid, solids and all that. So how does the sound travel? Okay, I'm going to explain the basic fundamentals about how the sound travels. Sound, actually it is called as a longitudinal wave. Now longitudinal wave. Now sound, it needs a medium. It needs a medium because sound cannot travel in a vacuum. I will come to that later. So longitudinal waves, it appears something like this. I will give a simple analogy. Let us assume that sound, it's some object, something like this, okay? And I am standing here and you are standing here, okay? I want to pass this sound to you. One way is directly throwing the pen on you, but that is not the way how the sound works. Okay, sound, it needs a medium through which it has to pass. Now let us consider these are air molecules, okay? Air molecules in that. It is something like this. When I produce a sound, it is like I give this object to the first molecule and then it transfers. Okay, it transfers and then it reaches to you. So which means the air molecules, it doesn't also move. I also don't move. The same way, even the air molecules doesn't move from here to reach you. So air molecule stays in a place, but it oscillates in a particular time period. Now this is how it is going to be. The air molecule, these dots are air molecules. Now we have seen in our school like these electrical waves we've studied, which is called sinusoidal wave, right? Now normally that is like a time period and this is the amplitude. That is how it is. The sine wave is plotted. Here I'm going to show the relationship between a sine wave and what actually happens in the air. Yeah. Now let us assume that, okay, this sine wave, it has a peak and a trough. Now here, this sine wave in this particular thing is going to be the pressure, air pressure, right? Okay, it's going to be the air pressure plot. Okay, that means when there is the air pressure is high in that region, we call that as compression, where the concentration of the air molecules are condensed. And when it goes to trough, there it is called as rarefaction, which means the air molecules are less distributed in that region. So it alternates compression, rarefaction, compression, rarefaction. And this is how the sound, which when I speak, it travels in the medium and reaches your ear. So this is just a simple analogy to make understand that sound is a longitudinal wave and it needs a medium for which the sound has to travel. Now, so that is the significance of the sound with relation to the medium with which it travels. Now coming to the second topic, frequency range. Now frequency range is going to be based on this. Now I mentioned that the air pressure, it is something like this. I'm going to talk about low frequency and high frequency. Okay. Now here, the low frequency, you can see the wave is spread. Okay, what is frequency? Now frequency is the inverse of the time period. Okay, F equals 1 by T. And here, this axis is a T. Okay, when the wave is expanded, that is the time period is high, then the frequency will be low. So we call this as a low frequency. And when this time period is less, then the frequency is going to be high. So we call this as high frequency. So what is the frequency range of an audio? Now audio, the frequency range is 20 Hertz to 20,000 Hertz, or we call it as 20 kilohertz. So this is the audio frequency range. Okay, this is the range of sound that our human ear can listen. Okay, it is not that the range is only this. There are frequency above this and below this. Now below this, whatever the frequency less than 20 hertz, their sound is present, but we cannot listen, and they are called as infra sound. And whatever is above 20 kilohertz, we call it as ultra sound. Okay, so this each infra sound and ultra sound has its own application, which you will be knowing later. So this is how it is. So air pressure, this curve in this particular period, we call this as atmospheric pressure. Atmospheric pressure. So which means when it is above the atmospheric pressure, it's compression. Below the atmospheric pressure, it is rarefaction. So this is how the sound propagation and the frequencies are related. Coming to the third topic, sound versus electromagnetic waves. See, we have seen the audio frequency ranging from 20 hertz to 20,000 hertz. Less than 20 hertz is infrasound. Higher than 20,000 hertz is the ultrasound. Let's now see the difference between sound versus electromagnetic waves. See, why I am talking about this difference between these two is for having a better understanding and to avoid some confusion which people have in general. Like, let me tell you, this is a frequency range, whereas for electromagnetic waves, the frequency range is 1 hertz to 10 to the power 25 hertz. Now, for example, what is the frequency of your alternating current? That is AC, that we have power at home, right? We call it as 50 hertz. Okay. Now, 50 hertz is somewhere in between. So people sometimes get confused. Oh, 50 hertz in sound and 50 hertz in electromagnetic waves. So how different are they? So that's the reason I just want to bring out the difference, and also to have a better understanding of what you see in general in life. Okay, sound is a longitudinal wave and it is a mechanical vibration, whereas electromagnetic waves, as the word clearly says, is a electrical, magnetic are involved, which means, see, here in the air we have seen the air molecules is just mechanically vibrating and the sound is traveling, whereas in electromagnetic waves there is an electrical wave and in the perpendicular there is also a magnetic wave. So electromagnetic wave is created in this fashion. So the second difference would be sound, it cannot travel in a vacuum, whereas electromagnetic waves can travel in vacuum. Sound, it cannot excite atoms, whereas electromagnetic waves can excite atoms. Now coming to this particular difference, vacuum. Now let you see in the night sky, right, and you see beautiful stars, millions of stars, right, studded on the dark sky background. Now you are able to see the light. Now light, actually it is part of the electromagnetic wave. Any other waves, for example, microwave, your telephone electromagnetic waves, ultraviolet rays, and the light, what we see, our eyes, we are seeing, right? Now the visible light. Now visible light, its frequency range is 10 to the power of 12 to 10 to the power of 15. That is the frequency range. So those are electromagnetic waves. So in the night sky, you are able to see the star which are millions of light years away, right? Still you are able to see the star. That is because electromagnetic waves can travel through vacuum. So that is outside the earth atmosphere, it's a vacuum, right? So that's why the electromagnetic waves, the light waves can still travel, whereas sound cannot travel. This is a big advantage. You know why? Because visually you can admire all that. Assume that there is a like a super star which is burst in the in remote galaxies, and assume that if the sound is going to travel all the way to earth, it will be a big confusion here. People cannot tolerate the sound that is coming from the outer atmosphere. So just remember, that is the reason we are not able to listen to the sound which is coming from outside. Okay, whereas we can see the electromagnetic wave, which is a visible light coming from distant star, we are able to see because it travels through vacuum. So vacuum in general, as I mentioned in my previous session, is nothing but Akash. See, one of the element which I mentioned Initially, where nothing was there, it was only the vacuum that was there. So from Akash vacuum, everything else was created. So that is one of the significance, and I hope you enjoyed this session. Thanks for watching this video. See you in my next lecture.